This is the last section, section 8. The ring of witt vectors with coefficients in a ring of characteristic B. Proposition 5. Let A be a ring of characteristic B for all the elements A and B of WA. For the positive integers m and n, we have for any tuple n. First relation is that when its characteristic B frobenius is just visible, it's just a component-wise raising to the power p. The second condition is that the frobenius composed with washibon commute, and the result is the first shift on the right hand side, and then you raise into the base power of each component. It's just step by step. And the third result is third relation is that you shift to m times, you shift A to the right m times, you shift to B, shift B to the right n times, you do the multiplication. It is the same as you do frobenius for A n times and do frobenius for B m times. You do the multiplication, then you do the shift. Well, for this one, not very satisfying proof is that you just check what is f0, f1, and fn. Do you realize it is? Okay, with characteristic B, it is just raising x0 to the power p, and here, same thing. So divisible by p here. Look carefully, you will see this is modulo p, okay? This 52 is just the result of 51 directly for 53 from formula 37, where we change B to VMB we have. Okay, so if you remember what is in 53 we have that's what we saw before without any condition on the characteristic of A. So you have this. Now you change B to VMB, we got this. So if you change the A here to F, frobenius acting m times, B, you change B to A. Okay, you change the index. Here is m depends on n, so there is n. Okay. We have this, we have this. And realizing this is true only when characteristic P, as we saw, right? You see, they commute. They do not commute in general, but they commute if it's characteristic P. And combining these two with this fact, we saw what? We saw that we got this here. Where we am acting on Frobenius. This is what we want to compute. A product with Fm, Vn, B. A product with Vn, Fm, B, but they commute, so they equal to each other. This equals Fm. This inside. We have a commutative in our case. This is it. The problem is what? There's no problem. We only want to say that the image of Vm multiply Vn is inside Vn plus n. This is important for us, okay? Okay. So proposition 6, let A be a ring for all integers k bigger or equal than 1. We have this. So what is V1? Okay. Vm A is image of Vm. What? What is this? It's just all the table is first. M position 0 and the remaining runs arbitrary. Ensemble. So as a set should be 0, product 0, and 4 product A as a set should like this, right? So V1 is just with WA, huh? So what we want to claim here is WA. You multiply with yourself k times is pk minus 1. VWA. You see, V says V1 multiply with V1 is inside V2. V2 multiply with V1 is inside V3. So after this times k times, it should be inside V, for example, Vk. And the right hand side is p times some power of p times v1. When he write like this, it didn't suppose the characteristic of A is 0. In the second statement, he supposes characteristic B. In this case, he doesn't assume the characteristic of A is P. We will see how do we prove A, for example. Let's see. To prove A, we use induction on K. The case K equals 1 is obvious. What is it? It's V1 A equals B to the power V1 A. So there's nothing to prove. Suppose P is bigger or equal than 2 by induction hypothesis, when hence this, and hence we want A to the power K equals P to the power K minus 2 multiply with V1 multiply with V1 squared. But we have this. What is this? This is V WA product V WA equals P times V WA. Where do we have this? The precise statement is V A product V B equals P V A product B. In this case is obvious. We have this, that is A product B surjective onto A. You can take A to be the identity of B. So this is true. We do have this. What can this bring us? What information can this bring us? Statement B tells us, suppose that A is a ring with characteristic B in the ring WA with ring, the V1 p-adic topology. V1 p-adic topology. And the p-adic topology coincide, and they are finer. Finer than the product C topology. This product C topology is the one we mentioned before, but we first see the first statement. Okay, suppose it is characteristic P, and we already have P equals for washable composite for Venice by 52. Come back to 52. 52 tells you we compose with F is F compose V, how it looks like. You see the first position is 0, so it's inside V1. Okay, it's inside V1, no problem. And then deduce from the statement A the inclusion. So P times W is inside V1A. The continued time in P is you continue multiplying P since V1 reason to the power of yes, okay, of course. Well, this is the same thing. Okay, WA is the whole ring. Of course, do the multiplication just to repeat and P times this by A. We have this. What does this tell us? We want A reason to some power K. It's containing the key of A. Here, if you're not careful enough, you may be confusing about the V1 p-adic and the C topology, where the Topology is given by the filtration, given by the ideas Vm, where Vm is Vm times Wa. Yeah, confusing. What's the different? And you even claim this one is finer than this one? This witt is finer than this one? Well, obviously they are different. What is different? We went adic. Well, the open the neighborhoods of 0 are v1 key. This means v1 multiply with v1 t times. Okay, and we end with k. What is with k? It is 0 product k times product with a. We know this is inside here by our relation. What relation? The relation that Vm product with Vn is inside Vm plus n. We just proved. So okay, it's inside. Okay, but it is strictly contained. You see? And this condition really tells you the p-adic topology equals the v1-adic topology, but v1-adic topology is not the standard topology, C topology. And if you have ever read about something about display, there he used the language IR-adic. In our text it should be called IA-adic, where IA is the ideal of WA, which is the, we see IA-adic means the v1-adic. It's the same thing. It says IA-adic compare with the p-adic to go inside. If P is nilpotent in R. So actually, you see here we say coincide. Actually, we see that if P is nilpotent in A, then it will coincide. But here we say its characteristic P is coincide. Okay, we could get something, the result strong. So we continue. The ideal consists of the elements when n is less than k. The first k minus 1 position are 0, and from the kth position on, every element is in the p to the kth power of a. This just comes from the formula 52, which tells us that Okay, this is obvious. It is hence fermé pour que la topologie C. Fermé is closed. For the C topology is the VM topology. You have to notice, you guys see something wrong. This notation, according to the multiplication by P, it's not a product with self. If it's a product with self, it's A self, because Y is inside A. But this just means all the elements of A raising to the pth power. Okay. It's this. So the problem is we have to say why this is fermé. Fermé means closed. Okay. They claim that the p-adic topology, the open subgroups PKWA, they claim they are closed. The closed subgroup in C topology. Why do you need this? Because there is a lemma. Okay, you'll see there is a fact. We write it clearly. Let's look at this result. You see, a GB abelian group. A is the topology, B is the topology, the linear topology, and G, which are given by the fundamental system neighborhoods of 0, AN and BN, where A and BN are subgroups. Okay, they're subgroups. In our case, we first have p-adic topology, and we have a C topology. C topology is given by the filtration, or you say the subgroups, open subgroups given by the VM, shifting to the M times, shifting to the mth position on the right direction of WA. Yeah, given by the open subgroups Pn times WA. Okay, so there are two assumptions. If each AN is open in B topology, if B topology is finer, in our case we know that p-adic topology is finer than C topology. The second condition is if each Bn is closed in the A topology, which means you have to prove that each Pm times WA as open subgroups is closed in the C topology. In our case, yes, well, to prove that, that's what we call Fermi. Then G is complete in the A topology implies G is complete in the B topology. So you have a finer topology. If your group is completely separated in a coercer, you want to know whether it is completely separated in a finer topology. Well, if you are complete in a coercer topology, you don't know if you are finer in a you're still completing a finer, because while you have a sequence, Cauchy sequence, your difference coming to 0, which means that they're very close to 0, which means that they're in the as small as you want the neighborhood of 0. But if your topology is very coarse, you see, as small as you can neighborhood of 0 is just very coarse. But if you take to finer, maybe you were in as small as you want, close to 0 in the previous topology, in the neighborhoods of 0, but if you change to a finer topology, maybe you're not anymore. So it's a problem whether you are completing a coarser topology, you in a finer topology. It's a problem. You start from coarser topology, you're complete, but you don't know whether you're complete. Again, in a finer topology, So this tells you it is if your open of the finer topology is closed in the coarser topology. Of course, we are not expecting HBN is open, because we know open subgroup is always closed subgroup. A closed subgroup may not be an open subgroup. It is an open subgroup also if and only if this closed subgroup has finite index. You just take its complement and using the coset of a subgroup to write it as a union of its cosets, then you will say you cannot expect that HBN is still open in AM, because otherwise it means they are the same topology. Okay, we see that we want to see whether they're closed. So back to our situation, we want to check whether this subgroup is closed in the C topology. Can you see, is it closed in the C topology? Well, we can try to prove this. For example, if you can prove that for example, P is it equal to the intersection of closed is closed for arbitrary. So you want to try to see plus what, plus V M. So for M, first we say, is this closed? Well, a little tricky. Let's see. I claim this is closed, as we already saw. An open subgroup is a closed subgroup. For example, if I take any element here, take X, this is open, that is also closed. Well, because this is open and closed, so this is closed. It's continuous. Stop logical group. Okay, stop logical group. Summation, multiplication, all continuous. This is closed. This is open. If this is open, this is the union of the open. It's open. But can you say it's closed? No, you cannot see. If there are infinitely many, you cannot see. But the problem is, for any fixed M, this is only a finite sum, right? Well, let's try to see like this. I'm feeling this is a little bizarre, but let's see. We just look at what is the complement of this. You see the same position, the 0, and then so on. This is Vm. This elements run over all the elements of A. Its complement is plus all the possibilities. So these are 0, then you plus all the possibilities here is 0, p to the power k, am, p to the power k. It's ai all in A, okay? This is it. You want to see whether this is closed. Well, this part really looks like the open subset containing this set. It's like the intersection of all the open containing itself. Well, this is not clear for me. I'm not sure if this is clear. So the problem, I restate, the problem is I want to use the lemma we just saw to show that the PK WA is a closed subset in the C topology. Hence, using the lemma, we conclude that since its WA is complete and separated for the C topology, it is also separated complete for the p-adic topology. But the problem is I cannot really prove this is closed in the C topology. Maybe we will solve it later. I will stop this video for this time.